Okay, here's your video lecture for section 6.2, Solutions of Initial Value Problems Using the Laplace Transform. So in this lecture we'll show how the Laplace transform actually does the trick of changing a differential equation or an initial value problem into an algebraic equation. And the way that it does this is it turns derivatives into multiplication, or in other words, it turns the transform of a derivative into multiplication via the transform of f. And so here's the theorem that tells us this, and we will prove this as an exercise. Suppose that f is continuous and f prime is piecewise continuous on any interval 0 to a. Suppose further that f is of exponential order, so you can take its Laplace transform with exponent a. Then the Laplace transform of f's derivative exists for all s greater than a, and it has this form here. Notice one can take the Laplace transform of a function's derivative by simply taking the Laplace transform of the function itself, multiplying by the new independent variable s, and then subtracting off the initial value of f. And one can extend this to higher order derivatives predictably. If you have the first n-1 derivatives of f being continuous and the nth derivative being piecewise continuous, with the first n derivatives being of exponential order with exponent a, then the Laplace transform of the nth derivative of f exists for all s greater than a, and you can write it as basically a polynomial in s, where the largest power of s, the nth power of s, is multiplied by the Laplace transform of just f, not even f's derivative or f's second derivative, and then all the other orders of s, or all the other powers of s, are being multiplied by the initial conditions for the first n-1 derivatives of f. And so with these two theorems, the theorem and a corollary, we're allowed to now take any differential equation that we'll encounter in this section and turn it into an algebraic equation. And we're very good at solving algebraic equations even before we learned calculus. Okay, so let's take this initial value problem here where you have y double prime minus y prime minus 6y is equal to 0, and then the two initial conditions, y of 0 is 1 and y prime of 0 is negative 1. If we transform the initial value problem on both sides, we'll have the Laplace transform of the left side equaling the Laplace transform of the right hand side. The Laplace transform of 0 is just 0, so you'll eventually get that result. The Laplace transform is linear, so you can split the Laplace transform of those differences there as the difference of the Laplace transforms. The Laplace transform of the first derivative of y is s times the Laplace transform of y, and then minus y's initial condition, which we know because it's an initial value problem. The Laplace transform of the second derivative is s squared times the Laplace transform of y, minus s times the initial value of y, and then minus s to the 0th power times y prime's initial condition. These values are determined by the statement of the problem, so they can be entered in, and then you can go ahead and end up with this equation after combining like terms. We can solve this algebraic equation and get this rational function for big Y. So we solve the algebraic equation. And that's instead of the differential equation. So we've solved an algebraic equation instead of a differential equation. And then finding the solution then is just transforming back or undoing the Laplace transform. And luckily there's essentially a one-to-one correspondence between functions and the Laplace transform. So we can apply what's called the inverse Laplace transform here and get little y. Okay, so the inverse Laplace transform is an operator such that the inverse Laplace transform of the Laplace transform gives you the function back, sort of this round trip theorem that you hear of throughout your mathematical preparation for this course. And so the solution to our example, and usually the inverse Laplace transform involves some algebraic manipulation and then the application of a table. The inverse Laplace transform of big Y here is going to give us little y, and after application of the inverse Laplace transform table, we end up with this as our solution. Notice one of the other benefits of doing Laplace transform is that you don't have to solve for C1 and C2 at the end of these problems, because that's taken care of in the application of Laplace transform, where you have the y prime of 0 and y of 0 embedded there. So once you inverse Laplace transform, you're done. That is your solution to the initial value problem. Okay, thank you.